Hello everyone, welcome back to the channel. Today we are diving into a crucial part of experimental design, which is to expose you on how you can set good factor limits. So here I'm going to give you a practical guide, a step-by-step procedure on the things you have to do before setting up a good experimental domain. Whether you are formulating or you are optimizing a process with different pricing conditions, know that your success will depend on how well you set good factor limits. So the question is, how can you set factor limits effectively? How can you do this effectively? To do this effectively, you need to start with the basics and gather background information. It's always good to gather background information. And you can get background information by consulting equipment manuals. Most equipment always comes with a manual, where in this manual, it defines the process or system's capabilities to tell you the maximum and the minimum operating conditions of that equipment. Knowing these conditions will immediately tell you where and how you can set good factor limits for your process or for your experiment. For example, an equipment may have a temperature range between 50 and 250 degrees C, or a mixer may have a speed range between 100 to 1000 revolutions per minute. So setting factor limits outside these ranges leads to unachievable or fail runs. It can damage the equipment or give misleading results. So knowing your factor limits or knowing your equipment limits will give you an idea on how well or where you can set the factor limits. Another way to get background information is to understand the standard operating procedures, because it will give you an idea on the safe, practical, and approved boundaries within which a process or equipment must operate. This will help us comply with standards and also avoid wasting resources, trying to force the system to operate at a region where it normally wouldn't operate. Another way you can get background information is to consult historical data. And this historical data can be from publications. You can get it from regulatory standards. Most countries always draw inferences from the Codex Alimentarius. After consulting literature and searching background information about the process or the product you want to formulate, the next thing to do is to define the design objective. Let's take this case study. A student who wants to formulate a functional food for the management of peptic ulcer disease. The student has defined the design objective for this dietotherapy. For it to actually be used as the dietotherapy of peptic ulcer disease, it must have an energy content ranging between 250 to 300 kilocalories. The protein content must be between 12 to 15%, carbohydrates between 50 to 60. The fiber content must be between 6 to 10%. The probiotic content must be between 10 to the 9 to 10 to the 11 colony forming units per gram. And the product must also have some specific micronutrients. This is actually a very complex design objective, and just setting the design objective will give us a new directive on the choice of uh, the factor choices, on the choice of factors to use, the choice of ingredients, the ratios of ingredients, the processing conditions, and the enrichment levels. You see, defining your design objectives, it summarizes what you have to do in your project. And to be honest, there is no single raw material or no single food product that can give us these design specifications. This means that you have to again consult literature and look at background information on the different raw materials that you can use. Different raw materials that have nutrients, where if you combine these nutrients, it will give you this dietotherapy. And if this specification was not given, or if this design objective was not already given, you can always consider looking at the Codex Alimentarius website to check the specifications of products, of food products. Or you can alternatively check from the regulatory body in your country, because each country always have a regulatory body that gives specification for food products. After setting up your design objective, the next thing to do is to try and know the potential factors. Here you can identify many factors that can potentially be used in your formulation. But at the end, you need to know that the more the number of factors, the more the number of experiments, and the more the cost of running the experiments. So you have to choose within the factors identified, the ones that are most significant, the ones that can significantly affect the process. You also choose based on availability, accessibility, and then the cost effectiveness of the factors. So here the student has decided to go with three factors: sorghum, soybeans, and fruit slurry. And the sorghum will contribute to the carbohydrates, the fiber, soybeans to the protein, and the specific micronutrients desired. The fruit slurry will contribute to the vitamins. And the limit of solution of the factors as defined by the student, and also based on the design objective, the student decides to go with 0.5, 0.85 for sorghum, 0.1 to 0.45 for soybeans, and 0.05 to 0.4 for fruit slurry. This is a typical mixture design problem which has a fundamental constraint which says that the sum of component proportions must always be equals to 1. And here I is equals to 1 to n. This means that the sum of all the mixture components, sum of all the mixture proportions must always be equals to 1 or 100%. If n is equals to 3 for three factors, x1, x2, and x3, it means that no factor combination, like no sample, should have component proportion greater than 1 or less than 1. For example, this means that the upper limit of these factors can never be combined together, because 0.8 plus 0.45 plus 0.4 is not equals to 1. It's not equal to 1. Then 0.5 plus 0.1 plus 0.05 is not equals to 1. So this means that in the course of designing your limits, you should always check out for whether, if you combine the upper limit of factor x and the lower limit of the other two factors, or the other limit of the other factors, depending on how many factors you have, the sum will be equals to 1. For example, 0.85 plus 0.1 plus 0.05. You see the answer is equals to 1. If you combine 0.45 plus 0.05 plus 0.5, the answer will be equals to 1. If you combine 0.4 plus 0.1 plus 0.5, the answer will be equals to 1. So this is how we set factors, we set factor limits for a mixture problem. This is another example of a design objective for a flour milling factory, which says that the gluten content must be between 30 to 35 grams. The falling number must be between 250 to 300 seconds. while the protein content must be between 12 to 14%. So again, you have to look for the factors, know the factors that can actually give flour with these quality specifications. And here, the engineer in charge has decided to go with ascorbic acid, amylase, and gluten. And based on the design specifications, the engineer has decided to go with these limits. Ascorbic acid should be between 3 grams to 15 grams. Amylase should be between 2 grams to 14 grams, while gluten content should be between 1 gram to 13 gram. And again, the sum of component proportion must always be equals to 100%. You see again that if you take the upper limit of ascorbic acid, the lower limit of amylase, and the lower limit of gluten, it will sum up to 18. If you decide to take the upper limit of amylase, the lower limit of ascorbic acid, and the lower limit of gluten, it will also be equals to 18. If you decide to take the lower limit, the upper limit of gluten, amylase, and ascorbic acid, it will also be equals to 18. So this is another example of a mixture design problem with limits. Let's have another example here, which is actually a process design example involved with the enzymatic conversion of biodiesel from triglycerides and methanol. And the objective is to optimize the yield, preserve enzyme activity, and minimize reaction time. So here the factors have already indirectly been given, which is the temperature, the catalyst, and the reaction time. So what you have to ask yourself to set the limits is at what temperature that can initiate the reaction. What is the highest temperature that if the reaction goes beyond this temperature, the catalyst will be destroyed? What is the least concentration of catalyst can be used? What is the highest concentration? What is the least reaction time that can initiate the reaction? And what is the highest reaction time that if the reaction is allowed to go beyond this time, side byproducts can be formed and contaminate the biodiesel. Based on what we have seen so far, we've understood that setting up factor limits isn't just guesswork, it's a science. So it's always good to think practicability and cost. In as much as you are setting your factor limit, it's always good to set factor limits that are practicable, are feasible, and they are cost effective. A good factor range should be such that it is easy to replicate, it is affordable to test, and it is not too wide, so you can always stay within the control limits. And if it is possible, I always recommend running preliminary studies so you can actually be sure that what you are getting from literature or what you have gotten from the technical data sheet is actually applicable or is actually possible in your own case. If you found this helpful, don't forget to like, subscribe, and drop a comment if you want to see a step-by-step design in action. Thanks for watching and see you in the next video.